All right, welcome back to another video. So this is a buoyancy problem, and a cube of 80 millimeter on a side is made of a rigid foam material and floats in water with 60 millimeters of the cube below the surface. Calculate the calculate the magnitude and direction of the force required to hold it completely submerged in glycerin, which has a specific gravity of 1.26. So over here on the left, we have given H is 80 millimeters, W is 80 millimeters, which is the width and the height. It's submerged below the surface here. If you notice, I have a sketch of 60 millimeters. SG for glycerin is 1.26. We have acceleration due to gravity, which is G at 9.81 meters per second squared. And then we have the density of water, which is rho, which is 1,000 kilograms per meter cubed. Now, we're going to look for this force to hold it down, and I'm going to do the free body diagrams. But what we have is two cases. Case one, this orange is your foam material floating in water. Okay? Case two is it's submerged right below the surface, and we're going to hold it there with a force. Okay? Now, what do we have for free body diagram? Well, let's use green here. What we have is probably, let's see, the weight force will be in the centroid of the whole body. I'll put W. And then the buoyancy force would be the centroid of the submerged section, which would probably be here. All right. So in case one, we just have the weight would equal the buoyancy force. But in case two, and I'll kind of draw them together here. And I don't know which one's bigger, but I'll just do, This would be the weight. This would be, going downward. And then going up is your buoyancy. And then we're holding it probably up here, we'll call FD. So that's the force that we're pushing it down in glycerin. Okay. So here is our given, our find, our sketch. Right now, we don't have to worry too much about assumptions, but we can get into the solution now. Okay. And what we're going to do is write Newton's second law. And we're going to do it on case one. And we're going downward. Downward is positive. Is that what we did? Yeah, that's okay. We'll do downward as positive. It ain't going to matter right now. So we have negative buoyancy plus W equals 0. So the buoyancy force equals W. Okay. Which I'm going to plug in below here. Come on. FB equals the weight of that, or the buoyancy force, because we don't have the density of the material. We don't have the mass, okay? We need to actually use the buoyancy force equation, which states rho of the fluid times volume submerged times G. Okay. This will equal the density of the fluid. The volume submerged is L times W times HS. And then it's times G. So the buoyancy force, or really the weight, right, is equal to 1,000 kilograms per meter cubed times, 80 millimeters times 1 meter. There's 1,000 millimeters times 80 millimeters times 1 meter. There's 1,000 millimeters times what was HC? 60 millimeters times 1 meter over 1,000 millimeters times 9.81 meters per second squared. So the buoyancy force, which equals the weight, is 3.77 newtons. Okay. All right. So we just did that because we probably would need that. Because in the second case, we need the weight, we need the buoyancy force equation, and we need, because we're looking for FD. All right, I'm going to do it right below here. Actually, you know what? Yeah, I'll do it right here. So let's find FD. Again, we're going to do Newton's second law. And downward is positive. So we have FD minus or plus the weight minus the buoyancy. Yep, equals 0. So FD equals the buoyancy minus the weight. Okay, and we have the weight of the object now from this first step that we did. Okay, the buoyancy force is different in glycerin, right? So let's write that equation out. It would be the density of the fluid times the volume submerged times gravity minus W. And I'm going to keep writing it down the page because it helps. The density of the fluid, if we know Sg, it's Sg times the density of water. Okay? That's this. Times the volume submerged. It's completely submerged and it's a cube. Okay? So it'd be H times W times L. That's the volume submerged times gravity minus W. Okay, and we can plug this in. FD equals, this was what? 1.26 times 1,000 kilograms per meter cubed. And this is 80 millimeters times 1 meter over 1,000 millimeters. And this is a cube, so I'm just squaring it because H, L, and W are all the same. Times 9.81 meters per second squared. And then minus, I'm going to use red here, 3.77 newtons, which is from that first step that we did that we weren't sure if we would need it, but we did it, right? If you started with this equation, with this step, you would realize you were missing W, and so you can go back and do the free body diagram and the sum of the forces in the case 1. All right, now FD, after this, everything comes out. You should get 6.33 newtons minus 3.77 newtons. So FD is 2.56 newtons. Okay, this is from that term. Okay, so let's just to recap. Case 1 is floating. Okay, we use that to find the weight. Case 2, we have to actually push it down in glycerin and we have to hold it there with an additional 2.56 newtons to get it to stay underwater. Okay, if you didn't, then it would float. And actually you could figure out with more calculations how high or how much it would be in the glycerin or how much it would be sticking out. Okay, you could. All right, so this is another good practice problem on buoyancy force. Goes through the equations, free body diagrams, sketches, and again, engineering format is key. You got to have givens, find your sketches, clearly labeled with forces. You don't start your solution until you see how the solution is below all of this? It needs to happen. You go down the page with a heading, with your equations. You plug the equations, plug the numbers in with units, and box your answer. Okay? Down the page, please. All right. If you have questions, let me know, and thank you.